Hi, I'm Brett Bickford, Managing Director of Generation and Transmission. Follow me on a tour of Rock Island Powerhouse One. Welcome to the inside of Powerhouse One. Rock Island has two powerhouses, and today we're going to visit the first one that was built on the Columbia River back in the 1930s. In the foreground you can see the first 4 units. What you're seeing here is the generators. They were built in the 1930s, and behind that were 6 units that we added in the 1950s. What's happening today in 2026 is we're finishing about a 20-year modernization program. Today we have an extra special feature of our tour. We're going to go down to a place that people haven't been since the 1950s. We're going to go down a long flight of stairs into a deep, dark cavern that we call the discharge liner, and it's about 80 feet under the water. So those very large beams that carry the whole weight of the unit sit in here on these big brackets. Here is what we call the stay ring flange. This is an embedded flange that the head cover sits on, and so water flows through here and into the unit, and then above here it's dry. And then those pockets are where the wicket gate servos sit that open and close the wicket gates to allow the water to flow. And we'll go to a unit that's assembled and you can kind of see what the difference is. But what's really extraordinary is if you look up on that flange, there's about 288 bolts that go all the way around there, and you have to line that up with all these mating parts that cascade down and cascade up. And so all that has to fit together within 1/16 of an inch everywhere. We're going to go out now into the intake water passage. Outside of this area that we've got closed off so they can sandblast and paint is what we call the distributor. That's where the water comes in and it gets distributed to this area here where the runner is. We'll see some steel structures called stay vanes that they're modifying to help turn the flow as it comes in. We learned in a hydraulic model that if we could turn the flow a little faster and guide it, that we could get about a 1% efficiency gain on the unit. So you might see some work out here where they're modifying stay vanes. Here's some of the stay vanes that they're modifying. They're adding a piece on here to help grab some of this flow and help divert it into the runner instead of it all going and stacking up in the corner over here. So they're helping split the flow off as it's approaching the discharge. It comes off of the runner in a big swirl. And as it's coming off and swirling, we want to try to break up that swirl and help guide it to go into the 2 discharge bays equally. And when we were doing the hydraulic model testing, we saw a larger amount of water trying to leave out of the south bay, and it's kind of like having too small of an exhaust pipe on your car. It was backing up and actually flowing around the sides and the roof and back over and back out the other side. And we could see that by putting strings on the wall, and the strings weren't going downstream, they were going partial or upstream. And so then we did change the hydraulic model with different features to get all those threads to flow downstream. Behind me are head gates, and that's what we install so that we can evacuate the water from this distributor area. Behind that's the river. We're down about 80 feet here. We use the intake gantry crane to install the head gates. And what these holes are here, that's where the wicket gate stem sits. And so each one of those holes, you have a wicket gate that overlaps, and those close and shut the water flow off, or open and regulate the flow of water to get increased power. The unit spins at the same RPMs all the time, but the wicket gates allow more water to get more horsepower. So the turbine runner sits about in this elevation. This is where it would rotate inside what we call the discharge liner. This is a metal liner. Behind that's the concrete. And after the phase of the work in the draft tube, they'll move here and they'll install what they call a boring bar. And that boring bar will cut this surface and make it larger, and we'll come back with a stainless steel overlay. And we'll lay that to help, that stainless steel helps resist cavitation damage. And then it allows us to machine then a round discharge liner for that runner to fit in to maintain that 1/8 inch gap clearance. So it'll be nice, perfectly round, so that water doesn't blow by the runner. We want all the water to be pushing on those blades to spin them, so we want a minimal gap. So here's where we transition from the steel liner to just concrete. And then this is really the start of the draft tube. And so the water's coming down in a big swirl, and then it comes down and we've got two discharge bays that the water goes out of. And this is where we're doing the modifications to get that 3% efficiency gain. In where you see the rebar is, that was kind of a dead pocket. And so water would get in kind of a back eddy in that dead pocket and slow the water down that's leaving. So we're cutting off that kind of dead zone so that the water is just forced to go straight out and into the tail race. So we designed a special unwatering system for B5 through 10 units so that we could evacuate all the water all the way down to the floor so people could work in here. The normal house unwatering system, the lowest you can get the water is about at this ceiling point. And so you can kind of see over there, there's a metal bell that's attached to the stop log. There's 4 of those across there, and that's what we use to draw the water all the way down to the floor. And then any leakage that's coming up through the draft tube floor drains, we pump into that pool there, and the 2 inner pumps of those 4 can pump that out to the tail race. So behind those stop logs is the Columbia River on the other side. This is an uplift drain. So we put this dam in the river, and it's got water all around it, but in here it's evacuated. So it's kind of like a boat, it wants to float. So we have to keep it founded, we don't want it to float away. And so we do that by having this concrete bond with the rock, and we do it by putting in post-tension anchors. We do it by the mass of the structure. But because some of this rock below us is fractured and water can actually seep in from the tail race or the forebay, it wants to put uplift pressure. And so to help relieve some of that uplift pressure to minimize the thickness of this floor slab, those are relieving hydraulic pressure. So this slab is about 4 feet thick. It was going to have to be 10 feet thick to overcome all of that buoyant force to be stable. And so to save time and to minimize excavating rock to go down even farther to place all that concrete, they put a bunch of uplift drains in the floor to relieve that. So that's why they're open, and that's why they're collecting that water and sending it over the side, because we need to relieve that pressure while we're working here.
Right outside of this,
Columbia River.
It's Columbia River.
You got a gate that's that wide, and there's the Columbia River.
That's how this gate is about that wide.
Yep. We'll go up on the tail race deck when we leave, and we'll kind of show you what that looks like.
And these just slide down into place. And
yep. So this part of the work should be done within a month.
Okay.
Middle of February, this will all be done, and they'll be moving all of this out and moving up to install the boring bar to do the discharge liner machining. So it's interesting, there's a drawing and photographs that showed that they made this as a complete form and set it in place, poured around it, and somehow were able to tear it apart and take it out. But they built them over on the shore over in the village. There's a picture that shows these draft tube forms being constructed. And then they brought them over and set them into place and then poured around and then probably tore it out. And then was left as the cavity. So yeah, the last time that this unit was in this dewatered state was when it was constructed in the early 50s. It hasn't been dewatered since then, nor have there been people down here working since then. So it's pretty amazing. Thanks everyone for coming out for the tour. Really appreciate your interest in learning about the design that the district did between about 2004 and 2006 to try to optimize the output of Rock Island Powerhouse One. We were able to improve the efficiency by about 10% by modifying the wicket gates, the turbine runner design as well as the discharge liner.